First midterm review problem. It's everyone's favorite kind of problem, 2D kinematics. I started out the midterm review with two 2D kinematics problems, and they're probably the most annoying problems on the whole review. So let's plow through this. The setup in problem one is that you throw a stone off a cliff, and we're given the initial velocity of that stone, and we're given the initial height. You've got some numbers in your review. I'm just going to use symbols. And the important thing to know about that initial velocity is that it's purely horizontal. So there's no y component. Let's start answering all these questions that the problem asks. The first question, part A, is to list the initial coordinates where the thing starts from. So we might as well identify our coordinate system as having the origin at the bottom of the cliff right here. And if that's our xy coordinate system, then the initial x position is 0, and the initial y position is the height, whatever number was given. I'll just write that symbol h. Now the next question is, what are the components of the velocity vector? So remember, with vectors, we can express vectors in several different ways. We can express them in graphical form by just drawing a picture. We can express them in magnitude angle form. So this one would have a magnitude v0 and an angle of 0 degrees. Or we can express them in component form. And that's what part B is asking for. So the component form would give you v0 for the x component and 0 for the y component. Now we want an expression for the components of the velocity as a function of time. And this comes from the first kinematic equation, v final equals v initial plus at. So we can plug in that expression for each of these in the x and y directions. But keep in mind that in the x direction, there's no acceleration. That's ignoring air resistance or any other forces that might occur. We're assuming they don't exist in this scenario. So the x acceleration is 0, and that term goes away. And we find that the velocity component in the x direction is constant. This rock or stone is going to travel at a constant speed horizontally the whole time. So that equals v0, which is the initial speed that was given to you. In the y direction, however, the y velocity component will change in time. It starts out at 0, but there is an acceleration. That acceleration is the acceleration of gravity, which has a magnitude of g, or 9.8, and has a direction of downward. So it starts out as 0, but this term is not 0. It equals minus g times t. So that's our equation for the velocity components as a function of time. The x component doesn't explicitly depend on time, it's a constant function. Question D, what are the coordinates or position vector components as a function of time? That comes from kinematic equation number 3. You can think of it as x0 plus v0 xt plus 1/2 axt squared. And same thing for y. And of course, several of these terms are 0 in each of the equations. In the x equation, x0 was equal to 0, and the acceleration was equal to 0. So we just get v0x, which is that number v0 given to you in the problem, times t, which is just the equation for distance traveled at a constant speed. The y component, y0 is h, v0y is 0, and ay is minus g. So those are our equations for the components of the position as a function of time. All right, so far we've just been able to kind of write down the answers to these questions. These questions are just kind of setting up the problem. They're not even really problem-solving types of questions. Parts E and F really are problem-solving types of questions. So let's go through our problem-solving procedure for kinematics to do E and F. Remember, our procedure was to write down the quantities that we know and write down the quantities we're trying to find, then select the appropriate equation to use. Okay, so we are given x0, y0, v0, x, v0, y. We know the x acceleration is 0, and we know the y acceleration is minus g. And we want to find the time to hit the ground. Oh, sorry, we know some other stuff too. This is all kind of information about the starting point, but we also know some information about the ending point for the scenario in part E. The ending point is when the stone hits the ground. So we also know that y final will equal 0. Hits the ground. Okay, so we want to find the time to hit the ground. And we need to select the appropriate kinematic equation to use. And remember, there's 8 of them, essentially. There's the 4 for x, and there's the 4 for y. And most of them are not going to be useful. In fact, none of them for x are going to be useful. If you might want to do this as an exercise. List those 4 equations in x and realize that given this set of information, you don't have enough to solve for time from any of those. So now go to the set of 4 equations for y and think about what information you have. And there's really only one choice, one option. So we're going to need to use this one. Essentially this, what we just wrote over here. I'm using our old notation. And I'll put in the values we know here. For scenario E, the final height is 0. The stone hits the ground. That initial height, or y0, whichever one you use, y0, y initial, means the same thing, is h, that number that was given to you. And there was no initial y velocity, there's the acceleration term, and now we can solve that for t. Just a little bit of algebra. Like so. Okay, that's the time to hit the ground. Now in part F, we're asking for the final velocity vector in magnitude angle form. So we can do that most directly by just plugging in this time we found into our equations for Vx and Vy as a function of time. So V final x, when we hit the ground, is this thing evaluated at the time we just found. But that doesn't even matter because in the x direction, that velocity is constant. And V final y is this expression evaluated at this time we just found. So if you want, you can plug in this expression, or you can just plug in the number you calculated directly. Now, this is the answer in component form, but that's not what the problem's asking for. The problem wants magnitude angle form. So the magnitude, you find that using the Pythagorean theorem. And the angle, well, let's draw a picture so we know what we're talking about with this angle. Here's a stone, it falls down, and by the time it hits the ground, its velocity vector is something like that. So that final velocity vector, I'll draw it again here. That final velocity vector is below the x-axis. So let's define our angle as being below the x-axis. And when we define our angle like that, then we can say that tangent theta equals opposite over adjacent. And I'll use the absolute value of V final y. And so theta is inverse tangent and to be clear, when you specify your answer, you should say that this angle is measured below the x-axis or below the horizontal. Okay, so we've now answered all the questions that were written in the WebAssign version of this problem. Now, on my exam, I might ask you an additional question or two about this problem. And some of the types of things I like to ask are, first of all, explanations. And I like process explanations and concept explanations. So I might ask you a process question like, can you explain in words your process for solving part E of the problem. And you would tell me, well, my process is that I write down all of the information I know. I identify my initial scenario as being at the top of the cliff and my final scenario is at the bottom of the cliff. Then I identify my unknown that I'm looking for, which is time. And then I look through all of the kinematic equations, all 8 of them, and I determine that the only one that will allow me to use this set of information to solve my unknown is kinematic equation number 3 in the y direction. Now I might ask you more of a concept question, such as why is the horizontal velocity component constant? And you could tell me, well, there's no acceleration happening in the horizontal direction. Acceleration is what changes velocity. So if there's no acceleration, velocity is not going to change, and this projectile is going to move at a constant speed in the horizontal direction. Whereas in the vertical direction, there is an acceleration that comes from the gravitational force, and the vertical velocity of the stone will change. Now, I might also ask you another computation kind of question, such as instead of finding the velocity vector when this hits the ground, find the velocity vector when it's at some other height. And so you could do that by finding the time it takes to reach a different height. Instead of y final being 0, maybe y final is 10 meters above the ground. And you would change the final height, get the time to reach that height, and then find the velocity at that height the same way.